Okay. Okay, good morning, friends, and welcome back to heat transfer. We are going to continue and wrap up radiation heat transfer today. Okay. So remember, in the last class, what we did was we definitely talked about a very common configuration, which is exchange of radiation between two annular surfaces or in the annulus of two concentric cylinders. So it was exchanged between the outer surface of the inner cylinder and the inner surface of the outer cylinder, both cylinders being concentric. And we derived an expression. Okay. But then we we said that this is an expression which is very widely used and applicable for a variety of problems. And we figured out that that expression is not just valid for two concentric cylinders. It can be used for two concentric spheres. It can be used for any two surfaces which are in an enclosure. So any two surface enclosure where the shape factor of one of the surfaces to the other is 1, right? F12 is 1, and therefore F21 is A1 by A2. Okay? And then we say that what happens when the surface area of surface 1, that is A1, is very, very small compared to that of A2. And when we put that, which means A1 by A2 goes to 0, we found that it reduces to an expression we all know from our high school, which is Q equal to sigma epsilon A1 T1 to the power infinity minus T2 to the power infinity. Okay. So therefore, the lesson was that this expression for radiation heat exchange that we knew so far before we came to this course is valid only for a certain very specific situation. But it's a very well encountered, widely encountered situation. For example, if I'm standing in an open field and I'm exchanging heat by radiation with outer space. Okay. To give you another example, let us say that, this is probably you have been studying refrigeration also as part of applied thermofluids, applied thermodynamics. On a cold winter night, clear winter night, by the way, okay, if you leave a shallow bowl of water and then come back in the morning, you will see that it has frozen. It has got refrigerated. And the question is, how did that happen, right? And probably you know the answer, that because it exchanges heat, because it's a clear night, there are no clouds. So it can exchange heat by radiation, or it can lose heat by radiation to the outer space, which is at a very low temperature. On a cloudy night, you won't, because the clouds will form an obstruction. It will shield. So this is an example where heat loss by radiation is important. It's a practical example, and where the expression of sigma epsilon A T1 to the power 4 minus T2 to the power 4 will be valid. Okay. So now, towards the end of the last lecture, we started this concept, which is the last topic of this course, which is called the radiation network analysis, network method. Okay. So we started off by defining a new parameter, which is called radiosity. Of course, irradiation we know, which is the total amount of radiation emitted by other surfaces, or maybe including or by the surface itself, if it has a shape factor with respect to itself. So it's the total amount of radiation that is incident on the surface, that is falling on the surface, which may be coming from other surfaces, including itself. Okay. Now, out of that, what happens? Part of it is reflected, part of it is absorbed, and the rest is reflected, assuming that the surface is opaque. Right? And the surface, by virtue of being at a certain temperature T, because the surface is at a temperature T, is also going to emit radiation, which is epsilon sigma T to the power 4. So therefore, what is the total radiation flux that is leaving the surface? That includes its own emissive power plus whatever it is reflecting, the fraction of the irradiation that it is reflecting. So epsilon EB, so which is the overall emissive power, plus rho times H. Okay. So therefore, what is the net radiosity? Is the total radiation that is leaving the surface. So that is J. What is the net flux, therefore, that is leaving the surface? It is what it gives out minus what it receives. So J minus H. Okay. Which is what you see here. And then we did some mathematical, arithmetical mumbo jumbo here, rearranging terms, etc. And we came up with this expression, EB minus J divided by 1 minus epsilon over epsilon A. Okay. So there's an interpretation of this. Okay. And this is what this network analysis, it was first proposed by somebody called Oppenheim. So it is also called the Oppenheim's network analysis. But what is the interpretation? The denominator can be considered is equivalent to a resistance, right? And the numerator is like a potential difference, right? Driving radiation heat transfer. So this Q that is leaving the surface, you can think of it that if it were a black body, it would have emitted sigma T to the power 4. But being a non-black surface, it does not emit EB, but it emits J. Okay. And J is definitely, it turns out to be less than E. Okay. What it emits. And why is there a drop? Because there is something called what we call a surface resistance. Okay. So this guy sorry, we call it the surface resistance. Now, friends, please keep in mind this is not a thermal radiation network, thermal radiation definition. Because EB minus J, the unit is not temperature difference, and neither is the unit of surface resistance degree C per watt. Okay. In fact, the surface resistance, the unit is 1 over meter squared. Okay. So keep that in mind. This is not a traditional thermal resistance network that we have studied for conduction and will study for convection. This is a different one. This is radiation network, Oppenheim's radiation network analysis. Okay. Now, if you think of exchange, between two surfaces. Okay. This is my surface A1 and is my surface A2. And then I have radiation exchange Q1 to 2. Okay. Now what would be Q1 to 2? Q1 to 2 would be whatever 1 gives out to 2 and whatever it receives minus whatever it receives from 2. All right. So what is it that 1 gives out? The total amount of heat? J1, A1, right? Because J1 is the radiosity, right? That is what is leaving the surface per unit area times the area A1. How much of it goes to A2 times F12? Similarly, what does it get back from A2? Same thing, J2, A2, F21. Clear? Once again, J1, A1 is the total radiant heat flux, heat, not heat flux, heat that is leaving surface 1. The fraction F12 of that reaches surface 2. So that is what surface 1 is giving to surface 2. Similarly, surface 2 also gives J2, A2, F21 to surface 1. The difference of the two is the net radiant exchange between surface 1 and surface 2. Okay. So what can I write? I can I can simplify this a bit and write it as J1 minus J2 times A1 F12. Why? Because reciprocity relation, right? Shape factor A1 F12 is A2 equal to A2 F21. Okay. So or Q1 to 2 is therefore J1 minus J2 divided by 1 divided by A1 F12. Look at this expression again. Similar expression. Okay. I can write it as something like this. If this is my J1, this is my J2, I can interpret it in this manner, right? I have a resistance which is 1 over J1 F12. Okay. So this friend of ours, this 1 over F12 is also kind of a resistance, and we call it the space resistance. Okay. There's almost some resistance because there's a space between A1 and A2 through which the radiation heat transfer is getting transmitted. The radiant flux is getting, or radiant heat is getting transmitted. Okay. So therefore, we have two expressions under radiation network. One is because the surface is not a black surface, there's a surface resistance as a result of which what comes out of the surface is not the black body emissive power, but something else. We call that surface resistance. And then what comes out of the surface to go to surface 2, there is an additional resistance which we call the space resistance. So therefore, if I have two surfaces from Q1 to Q2, I can write that Q, or basically what I can do is I can define the overall resistance network in this manner. This is EB1 J1 J2 then EB2. Okay. What are my resistances? The first resistance, 1 minus epsilon 1 divided by epsilon 1 A1. The second resistance, 1 over A1 F12. The third resistance is 1 minus epsilon 2 divided by epsilon 2 A2. These are resistances in series, and this is this Q. Okay. So therefore, what can I write? I can write Q 1 to 2 is going to be EB1 minus EB2 divided by 1 minus epsilon 1 over epsilon 1 A1 plus 1 over A1 F12 plus 1 minus epsilon 2 divided by epsilon 2 A2. Okay, or sigma T1 to the power 4 minus T2 to the power 4 divided by this denominator. Okay, so this is more of a tool. Okay, doesn't give you a lot of physical feel of what is actually happening, but you can use it. This is a very handy tool. Let us see how. We have already done some examples, right? One, infinite parallel plate. Okay, right? So epsilon 1 A1 T1, epsilon 2 A2 T2. Okay, what do we know? We know A1 equals to A2. Let us say equals to A. F12 equals to F21 equals to 1. Okay, please put this. What is my Q? Sigma T1 to the power 4 minus T2 to the power 4 divided by 1 minus epsilon 1 A1 plus 1 over A1 F12 got it. Now we know A1 equals to A2 equals to A, and all these A's are here. So let me take it out and say key Q by A 1 to 2. Let's do some simplification and use the fact that the shape factors are equal to 1. So what do I have? 1 over epsilon 1 minus 1 plus 1 cut 1 over epsilon 2 minus 1. Please check. This is exactly the relation we had derived also by doing that ray tracing analysis. Okay. Remember, I was telling you that there's a very simple way to come to this expression, but it is not going to give you a feel of what is happening. That's why I did that physical exercise. Otherwise, just to solve problems, you can use this. You should use this. but I wanted to derive it from the physical explanation point of view. Okay. Number 2. Radiation shield. Let's do that. Epsilon 1, A1, T1. And then I put in a radiation shield over here. Let us say this is epsilon 3 on this side. Epsilon 3 prime on this side. Okay. Of course, epsilon 3 can be equal to epsilon 3 prime. So what do I have? I have EB1 and EB2 at the two ends. Clear? J1, J3, EB3. Okay, because it's the same temperature. J3 prime, J2, and EB2. Okay. Because remember, we have to see how the heat is flowing. From here, it comes to surface 3. Then, sorry, I think I did a mistake. EB3, the prime should be the top surface is E3 prime, huh? Not the bottom one. Okay. From here, then from here. Okay. So this is my Q. So I can write Q by A (1 to 2) EB2 minus EB1 minus EB2 divided by 1 minus epsilon 1 over epsilon 1. Okay. Plus 1 over F12 plus okay. So all these shape factors are all 1. And so what you finally get is sigma T1 to the power 4 minus T2 to the power 4 divided by 1 over epsilon 1 plus 1 over epsilon 2 minus 1 plus 1 over epsilon 3 plus 1 over epsilon 3 prime minus 1. Okay, so f 3 2, okay, not 3 1, 3 prime 2 and f 1 3. Okay, and if epsilon 3 equals to epsilon 3 prime, which is emissivity on both sides of the radiation shield is the same, compare this with what we got, exactly this expression. Okay. How about annulus? Two concentric cylinders, which we know can be anything else also. Cylinders, spheres, concentric or non-concentric does not matter. There are also what I can write exactly the same. I'm not writing it anymore. I'm not drawing it anymore. That okay? Let me draw. Why leave it? Yeah, sorry. Red for the surface one. Blue for surface two. So what can I write? Same expression as for the two bodies, like what we had done before. EB1 minus EB2 divided by 1 minus epsilon 1 over epsilon 1 A1 plus 1 over A1 F12 plus 1 over epsilon 2 epsilon 2 A2. Now F12 equals to 1, we know that. Okay. So sigma T1 to the power 4 minus T2 to the power 4. Okay, I'll keep that over there. And what I will do is I will multiply both numerator and denominator by A1. So what do I have? 1 over epsilon 1 minus 1 plus 1, right? Plus 1 over, sorry, I multiplied both numerator and denominator by A1. So therefore I will have A1 over A2 sorry, one note misbehaved. It does, as you know. Okay. I'll write it again. Or sigma A1 T1 to the power 4 minus T2 to the power 4 divided by 1 over epsilon 1 plus This is exactly what we had also derived. See, so we probably spent more than an hour to derive these three, which we could have done very easily by resistance network method. But this is a mathematical tool, and what we did during that exercise was to physically understand what was happening. This repeated reflection, how the energy gets split into something that is absorbed, something that is reflected, and and also the amount of energy that gets reflected from surface 2, part of it comes back to itself and part of it goes back to 1. So all this physically what happens, that we could not, that feel we wouldn't have had we only done this network analysis. Okay. Now when network analysis becomes very helpful is multi-body enclosures. So let's take a 3-body problem. Okay. A 3-surface problem. I should not be using body. I should use the 3-surface problem. Okay. So 3 surfaces. Exchanging heat with each other. Okay. Random surfaces. 1, 2, 3. Okay. A1, A2, A3. Okay. So here, what we can do is, it is no longer, something that it's like an electrical resistance, right? So let us write E1, EB2, and here EB3. Suppose everybody would have their own surface resistances. So J1, J2, J3. Hmm? 1 minus epsilon 3, epsilon 3A3, 1 minus epsilon 1, epsilon 1A1, 1 minus epsilon 2, epsilon 2A2. But then what happens? J1, the radiosity from A1 can go to A2 and A3. Okay. So I would have a space resistance between 1 and 2. And I would also have a space resistance between 1 and 3. This is 1 over A1 F12. This is 1 over A1 F13. Similarly, J3 will also, J2 rather, will also have exchange with both 1. Space resistance is exactly the same. A2 F21 and A1 F12 are the same. And here again, you have 1 over A2 F23. Okay. So Q 1 to 2 would be J1 minus J2 divided by 1 over A1 F12. Q1 to 3 Okay. If you look into this, I want to find out what are these three? Like just a current, like an electrical circuit. Okay. So probably you guys know better. I mean, you have done much more recently, very complex electrical circuits. But if I give this to you, and I say this is Q12, this is Q13, and this is Q23, like I1, I2, I3, would you be able to solve this?
Yes.
How? What are the unknowns? Let us look into this. Three unknowns. Which are the radiosities? We don't know, right? K1, K2, K3. Okay. So, okay, now tell me, my friend, how would you solve this?
Probably convert the network from delta to star.
Okay, that's one every year the students tell me. Yes, I also remember star delta conversion, but I've completely forgotten that. Okay. So yes, I'm sure you can do that. Any other method? Can we use Kirchhoff's current law?
Yes, sir. Current law, voltage law, either.
Right. So let's use Kirchhoff's current law. So which means that the total current coming to a node, the sum total is 0. So use Kirchhoff's current law at each node. Sorry. Okay, which means the sum of currents entering the node is 0. Entering the node. Okay. So let's take node 1. What is the total sum of current that is entering the node? Is something that is coming from here. Something coming from here, something from J2, something from J3. Similarly, okay. So what can I write for node 1? I can write EB1 minus J1 divided by 1 minus epsilon 1 divided by epsilon 1 A1. Okay. This is coming from EB1. Then something will be coming from J2, coming from J2. So I have to write it in this manner. Now finally, whether it will be positive or negative, that the circuit itself will take care. So A2, F21. I can write A1, F12 as well, plus J3 minus J1, 1 over A3, F31. This is 0. Right? Okay, write it for the node 2, J1 minus J2, 1 over F1, A1, F12, plus J3 minus J2, 1 over A3, F32, sorry, 2 F23, plus EB2 minus J2, 1 minus epsilon 2 divided by epsilon 2 A2, 0. J3, again write the same thing, J1 minus J3, 1 over A1 F13 plus J2 minus J3, 1 over A2 F23 plus EB3 minus J3, equal to 0. So look at this. 3 equations and 3 unknowns. So definitely we can solve it. So this is how we do it, and up to 3 we can do algebraically. 3 unknown simultaneous equations with 3 unknowns, 3 equations, 3 unknowns, we can solve algebraically. When we go to 4 or 5 or n, then we need to take help of computational tools, okay? Like Mathematica, Maple, these kinds. Okay, or if you know the, and if you know the values, then you can even use matrix inversions and you write your own code as well. Okay, so this is what it is. What I would request you is, please look into some solved examples and solve 1 or 2. I mean, there are, if you go to any textbook, there will be either problems or examples. Do 1 or 2 yourself, and then there's nothing here. Okay, I mean, you have solved much more complex network analysis. Now, I would just write 2 things. Two special cases. One is called a re-radiating surface. What it essentially means is it's an insulated surface. Okay. What does that mean? That means that 0 heat flux. And J is therefore equals to EB. Okay. So this is called a re-radiating surface. Note that 1 minus epsilon over epsilon A is not equal to 0. May not be, not necessarily equal to 0 at least. And then there's a case B, where it's a very large surface area. Okay. So what does that mean? It means that A tends to infinity, or 1 minus epsilon over epsilon A equals to 0, and which again implies P equals to EB. Mathematically, they are equivalent, but physically they mean completely different things. One is a huge surface area, so surface resistance is very, very low. You can neglect it compared to the other resistances in that network. Okay. In the other case, it's a re-radiating surface. Whatever comes, it's insulated, so nothing goes into the surface, nothing gets absorbed, and whatever comes is reflected out. Okay. So in such case, the network becomes, let's say, A3 is such a surface. Okay, either A or B. So what you will do is, the network therefore becomes EB1, J1, J2, EB2, and here J3 equals to EB3. You don't have anything else. So whatever comes in, so what does that mean? Q1 to 3 equals to minus Q2 to 3, or equals to Q3 to 2. So whatever it receives from 1, it sends back to 2. Okay. So whenever if you read a problem where say surface 3 is a re-radiating surface, or surface 3 is an insulated surface, or surface 3 is much larger compared to A1 and A2, it means from network analysis point of view, J3 equals to EB3. Surface resistance is 0. But keep in mind, for re-radiating surface, it essentially does not mean surface resistance equal to 0. That's why I wrote here that 1 minus epsilon over epsilon A is not equal to 0. But because the surface characteristic is such that nothing is getting absorbed or stored. Whatever comes, leaves. Okay. All right. So that brings us to the end of the topic on thermal radiation. We covered quite a bit. And for the sake of this course, see, any of the heat transfer topics are huge. Okay, people have spent their whole lifetimes on that. But from the undergraduate heat transfer course point of view, I believe these are the most important concepts that have been covered, right from emission characteristics, then incident or irradiation characteristics, okay, which is absorptivity, reflectivity, and transmissivity. We did not deal much with transmissive surfaces. Okay, then we talked about radiation intensity, solid angle, the directional nature. Okay, under emissive power, we started with the laws of blackbody radiation, which is Planck's law, Wien's law, and Stefan Boltzmann law. And then after we got equipped with all this fundamental knowledge and these tools and properties and expressions and laws like Kirchhoff's law, Lambert's law, etc., we went ahead and started doing problems that would enable us to calculate what is the radiant heat exchange between two surfaces at different temperatures. Okay, and while doing that, we got introduced to something, a very important concept, which is shape factor. Shape factor basically is how much can I see you? Of all the things that I can see around myself, what is the fraction of you? Okay. It's like I have some things and I want to give it out uniformly to everybody around me. So what is the fraction that you are going to get? Well, that depends on how close you are to me, how much I can see you, how visible you are to me. Okay, so similarly, so this shape factor becomes very important, and we also did some problems on shape factor calculation. Right? There are certain properties of shape factors which are important, based on which we can calculate shape factors between two surfaces. Okay, without going through the double surface integrals. Okay, and finally, we came up with a few examples of exchange between real surfaces. We looked at 3 examples very elaborately between 2 infinite plates, then the problem of introducing a shield, and then the problem of concentric cylinders. But later, when we did the thermal resistance network, we figured out that, just using this mathematical tool, all those heat exchange numbers can be calculated pretty efficiently. However, we do not get a feel for what is actually happening inside. Okay. It is not like an electric current. Electric current, you look at a circuit, you can also visualize. There is some wire going on. There is a current through that. There is a resistance, additional load resistance, or just a resistance due to the wire, etc., etc. But in thermal radiation, it's not so easy. Right? It means a lot of things. When you say there's a net heat exchange between J1 and J2, it means a lot of things, right? It means repeated reflections, absorptions, etc. So that's why we elaborately looked at those example problems. But finally, we learned the Oppenheim's radiation network analysis. Okay, so with that, we come to the end of radiation heat transfer. And I will upload the problem sheet today. Please go through that. And hereafter, we are going to move on to another topic from Wednesday. It will be either convection or heat exchangers. I will see, because from Wednesday till next Monday, which is when we break for Durga Puja. I'll see if we can cover heat exchanger. Okay. And during Durga Puja, what I will do is I'll give you a reading exercise, because otherwise we won't be able to finish. The reading exercise is not much. It is about brushing up your fundamentals of fluid mechanics. You already know this, but you need to go back and learn those. I'll see if I'll either record those lectures and share with you, or I will share my notes with you. Okay, either way, if you go through them, you would have brushed up your fluid mechanics knowledge, and then we can directly go to convection. Okay. All right, thank you very much, and I'll see you again on Wednesday at 8 a.m.